All right, so in these two videos, we're going to look at more related rates problems. So just kind of new applications of related rates. So we mainly focused on perimeter and area and some right triangle stuff. All right, so now we're going to look at some other things that we can do with related rates. All right, in this specific video, we're going to look at volume. All right, so one thing to note, when you're performing related rates problems, it's important to think is what is changing and what is constant. All right, sometimes there'll be some things you can plug into your equation at the beginning, and that makes your derivatives easier. So if something's not changing in the problem, it's not going to be affected by rate, so you can plug it in before you do derivatives. If it is a quantity that's changing, you can't plug it in at the beginning because that kind of represents that it's not changing. All right, so just kind of think about what is not changing in this problem and what is changing. That'll kind of help make the problem simpler. All right, so here's our first example. We have a cube being filled up with water at a rate of 10 cubic inches per minute. All right, each side of the cube is 5 inches. How fast is the depth of the water changing? All right, so I'm going to quickly draw a picture, and then we can figure out what's changing and what's not in our picture. All right, so this is the situation we have. We have this cube, it's a perfect cube, where every side is 5 inches. We're filling it up with water, and we want to know this quantity. How is the height of this water changing over time? All right, this is a volume problem because we're pouring this water in. We're kind of taking up more space in this cube. So the first thing to do is figure out, we're looking at volume. All right, so volume, what is the volume of this cube and kind of what's constant, whatever. So the volume of a cube is kind of the three sides being multiplied together. But the volume what we're talking about isn't the volume of the whole cube. It's just the water part that's filled up with the cube. So whatever we think about is the volume of the water. All right, well, it has this square base. All right, and the square base is never going to change. So the volume is always going to have these two 5s. All right, they're not changing, so I can put them into the equation at the beginning. But the volume of the water is changing in the height, because as I pour in more water, that height's going to change. So I can't plug anything in for that h yet. All right, so the volume of the water is going to be 25 times h. All right, we don't know what h is, we don't know what v is, but this is the relationship between the volume of the water and the height. All right, now that we have an equation, now we can switch to our rates. So we take our derivatives, so dv dt equals 25 dh dt. We're trying to figure out how the height's changing, so we're not going to be able to plug that in. So we should be able to plug in something for that. And we do know how the volume's changing because I'm putting in 10 cubic inches of water. All right, so that's going to change the volume of the water in the cube. And then we know that that rate is 10. And then we just need to divide. The change in height is going to be 10 divided by 25, which is 2/5 cubic inches per minute. So, because it's the same unit as how the volume's changing. Oh no, it should be inches, just inches per minute, because height is just one-dimensional. All right, so our height is changing as the volume's changing. All right, and again, you can kind of see when something's constant, something's not changing, it's just going to get plugged in at the beginning. So these 5s are never going to change because those are the kind of square base of the water. So those are never going to change. So I put those into the original equation before I do derivatives. All right, if you didn't do derivatives, you'd have these like 3 separate variables to work with, and you're taking derivatives, and that's really complicated. All right, so you want to do if anything's constant, all right, plug it in first and then do derivatives. All right, sand is being poured into a pile at a certain rate, and the pile of sand forms a right circular cone. All right, so that's going to be the shape we're talking about in this problem, a right circular cone. Another important information is the radius is equal to the height. So that'll help us as well. All right, how fast is the height changing? Oops, let's use a different color. How fast is the height changing when the pile is 5 feet tall? All right, so this is all the important information. We're working with a right circular cone. The radius is equal to the height, and we know how fast the height is changing. All right. So if we look at a picture, this is a pretty simple picture to draw. We just have this kind of pile of sand. And we know that the height here is the same as the radius there. And again, as sand's being poured in, the pile is going to expand, the volume is going to get bigger. So again, it's a volume problem. We need to find out what the volume of a right circular cone is. This isn't something I expect you to have memorized, so you could just Google this. It's 1/3 pi r squared h. All right, so that's the volume of a cone. All right, we know something about volume, so we're going to leave the v there. We care about the height, so we're going to leave the h there. But right now it's kind of complicated because we have this r squared and this h. But we make the problem a lot simpler because we know in this example, the radius is equal to the height. So we can just replace the v with an h because they are equal to each other, 1/3 pi h cubed. All right, so this is our formula. Our volume of this cone is 1/3 pi times the height cubed. Again, I don't want to plug in 5 for my height right now because the height's going to be changing throughout the whole problem. It's not constant. I can't plug it in until after I do derivatives. So now I can do derivatives, dv dt. That's the simple one. On the right, again, 1/3 pi is just a constant. So if I'm just going to multiply that by the derivative of h cubed. So I bring down the 3. That'll cancel out with the 1/3 pi h squared. And I took the derivative of h. I'm going to get dh dt. All right, so again, just remembering how to take derivatives, and then just remembering that this 3 is going to come down, and then you subtract 1 to get h squared. And then after you take the derivative of h, you have to get that dh dt. All right, now we plug in everything we know. How is the volume changing? Well, I'm pouring more sand in, so the volume is going up at a rate of 8. Right, pi is just a number. h squared, at the exact moment I care about, the h is 5, so that's the current height. And I don't know how the height's changing yet. But now I do know how the height's changing because I just have to divide. The height is going to be changing at 8 over 25 pi. And height is one dimensional, so it's going to be feet per minute, per second, because that was the unit we had up there. So it'd be feet per second. All right, so you can see the kind of process of making the equation you care about, or when you're adding something to something else, that's going to be changing the volume. So that's kind of the main formula you use. Use your volume. Right, plug in anything that's not changing first, or in this case, there's nothing that's not changing. The only thing that's kind of not changing is that the height is equal to the radius. All right, then we do derivatives, and then we plug in everything we know to get our final answer. All right, so these are kind of volume applications of related rates. All right, they all kind of work in a similar way, but you recognize their volume when you're kind of adding or taking something out of some type of container.